Think we're live?
Oh,
Yeah, we're live.
All right. Good afternoon, everyone. Welcome to Corecast. I am your host, Tim.
I'm Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Corecast. Before we get started, if you haven't already, do join the Discord channel. And if you're watching this on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode. So let's get to it. So at Tim and Mikey, we got this request to do this episode from a fellow viewer about virtual particles. I guess like before we kind of get into the nitty gritty of it, I guess what does it mean to be like a real versus like a virtual particle? Like, or what is like a particle in general, if you were to like break it down to a layperson?
Go, Tim. That's a tough question. I'll follow your
Yeah,
lead.
yeah, I can get started on this. I think we did a previous episode on probably a few episodes on particles. What particles are these intuitively these are these distinctive objects like electrons, quarks, protons, or neutrons even. Um, that have some distinctive properties, and the typical properties are a particle can have mass, can move at different speed, it can have specific charges, it can have particular spin. I think one of the previous episode mentioned that. So there's a whole host and categories of properties associated with a particle. So I think at the most basic level, particles are like a very consistent and individual entity at which we can study physics from.
Gotcha. So would you say they're like, could I consider them to be units of like, or are there entities that have specific properties associated with them that are consistent
Yeah,
when we
yeah, yeah.
measure them?
Exactly. I think I
Yeah, I
forgot
think
some of the some.
that's a very generalized definition, right? Like, I don't know. I mean, should we start like so? When most people think of a particle, they think of like the building blocks of everything, right? Like atoms or protons make up atoms, quarks make up protons, and they're kind of like we like to think of them as the building blocks of like all matter. I guess in our previous episode, we kind of discussed that in particle physics, they have kind of more generalized definition in the sense that they're not just the building blocks of matter, but they can also transmit forces. And basically any kind of phenomenon that you see can be attributed to some kind of particle.
I see. So okay. So, oh, Tim, were you going to say something?
Oh yeah. Well,
Oh no, I was okay. Go.
yeah. I was just going to add that even though we might have this sort of abstract definition, this is actually very close on what people intuitively think of particles, right? Like these distinctive properties is what allow us to go into the lab, grab a particle, and study it, and kind of separate it from the rest of the environment, and say that hey, there's a particle there. So these distinctive properties and location could also be one of them. We can isolate them, look at its motions, look at its location. So like a particle is not like a particle could not possibly be, for example, on Earth or and also in the galaxy next door, right? Although with some caveat,
Yeah, there's some caveats to that.
with some caveats, yeah. But these general properties that particles have is what enable us to talk about particles intuitively. Right? So this is not like abstract pie in the sky.
Well, I think that's a
Gotcha.
good generalized definition. A distinct entity with consistent properties. Let's start with that.
Okay. I guess what makes something distinct? Like, how do I say it's distinct?
Well,
Is that obvious or yeah?
it's not obvious. First of all, it has to be predictable, right? Like, for example, if
Mhm.
I grab a proton right now, I know for
Mhm.
sure that it has a particular mass in
Mhm.
some unit. Probably it would just have one, I don't know, atomical unit, one proton mass. So if I grab another proton tomorrow, it's not going to be twice as heavy, like otherwise physics will go crazy, right? Like the mass of the proton is the same. If I grab a proton today and make hydrogen out of it, I can, I don't know, put it in a hydrogen fuel cell and drive around with it, right? Like I don't have to I don't have to think about proton today versus proton tomorrow. Yeah. So I think these are the yeah. So these are some of the properties that it's just so obvious to us. I think we just take for granted, basically.
So
Yeah,
I guess
so like I guess this distinct in terms of these consistent properties, right? As Tim mentioned, like a certain mass or a certain charge one would be attributed to a proton, another mass, an MeV, and mass one would be attributed to an electron. And these are consistent, and the fact that they're consistent is what makes the distinction possible between the two.
I see. So what if you noticed that there was like a quote unquote like particle for like I'm using quotes, particle in quotes that had like all of the same other properties, except when you picked it today and you picked it tomorrow, one of its properties changed, like same mass, it became like 50% heavier. Like, has that case ever arisen, or like what would you say about that?
I would say typically
Okay,
no.
well, I guess
Yeah.
Well, actually, that's kind of going to lead into. We should probably say the discussion pro because it kind of leads into what we're going to talk about later. But I would ask you to do another experiment. Like if you measured a third day and a fourth day and a fifth day, is it constantly changing in some continuous manner, or is it like because if you measure it to be one mass today and then another mass every day after that, I would say that you found a different particle.
That makes sense. That makes sense.
If it's different, is it consistently different? If it's not consistently different, then you might say, okay, it's the same particle. But if it's consistently different, then that would be enough, I think, to distinguish it as a separate species of particle.
Gotcha. Okay, so I guess coming back to the original topic of this episode, virtual particles. I guess like what are they? Are they like these distinct entities that exist inside a computer, or is it like something broader than that?
Yeah, I think first of all, to understand virtual particles, you have to first understand, instances where some of these consistency could be a little off, basically. So things like charges and so certain things don't tend to be inconsistent. For example, charges, it's either +1, -1, or some other number. You can't really have like 1.1, for example. I mean, with some caveats, of course, experimentally, things could differ. So one of the things that could become inconsistent is the mass, what you mentioned. And experimentally, people notice that when they measure particles that are unstable, for example, the neutron, for instance, or other particles like the Higgs boson, and it turns out that the more unstable they are, the more variation they have in their mass, right? So this is kind of the first hint that, hey, look, the line between a particle having consistent property and not is a little blurry there.
I see. I guess so. Tim, you're drawing special attention to mass as like the property that changes. Why that particular property? Why not like I don't know some of the other properties like charge and stuff like that? Is there like a deeper reason?
Yeah, I think mass is something that's kind of continuous. Charge is more like a category, so you can't really deviate. You can't really have like a small deviation from the charge. But for mass and energy in general, you can have small deviations of it. So
yeah, I guess that is a deep reason, right? The fact that energy is a continuous variable and charge is a discrete variable. And in the theory, these can be attributed to differences in the symmetry. So that's kind of like a hard rule that charges are discrete. They come in discrete units of +1, -1 typically. And energy can be continuous. So there's some wiggle room there for your measurements to vary.
That makes sense. Okay, so mass and energy, these continuous parameters, there's a little bit of differentiation. So I guess Tim, you were saying along those lines that like there can be I guess like a more unstable particle is the more variation in measurement of mass. Did I understand that correctly?
yeah. And generally that variation is not random, right? Like it's not like if I pick a Higgs boson today versus tomorrow, it's going to be like 20 times heavier or like 1/20th of the previous day's mass. They tend
It
to
might be.
fluctuate.
You get unlucky.
Right. If you get really unlucky. But what it is there's some statistical distribution that peaks around what we actually call the true Higgs mass, which is about 125 times the mass of proton. But then it turns out that there's what we call this width. There's this mass width. And if you pick another Higgs boson tomorrow, you might get 124. And then the day after, you might get 130. If you get really unlucky, maybe you'll get 300 or something. So it turns out that, the idea of the Higgs boson having a right mass, it's kind of a little fuzzy there. So, but then we can understand it in terms of quantum physics. And so this is where the concept of virtual particles, I think, start to emerge a little bit.
Yeah, let's just say something really confusing and then just unpack it. So the mass of unstable particles follows a bell curve. It has some consistent average, let's say, and when you measure it, it'll typically tend to be measured around this average value most of the time. Very rarely you'll see it deviate a lot, but it's the bell curve basically.
So before we dig into virtual particles, how do we know this isn't just a function of measurement error? Like it's all measurement error, and like that the mass is actually like a true value, even if the particle's unstable.
Great question. I think Tim could be the one to handle this.
Yeah, I mean, of course, when you do a measurement, you can always break it down into experimental error versus theoretical error. And if you notice that, hey, my experiment just got 20 times better, and I'm still measuring this bell-shaped curve, although it's not exactly bell-shaped, but it looks like a bell shape, roughly speaking. Like even though you improve your experiment so much, you're still observing this fluctuation. Then this fluctuation becomes irreducible. Like it's not a function of how good your experiment is. It's just the fact of nature. So at some point, you realize that, and this is kind of a universal property for every particle that's unstable, basically. And then you start realize that, hey, look, the mass as a quantity just isn't exact, right?
I see. So just to clarify this further, if you had a particle that's stable, for instance, like take the electron or, arguably even the proton, but let's say electron, for instance, and you do experiments to measure its mass, the error of its like mass measurements will go down as your experiment gets better. It won't there won't be some like irreducible uncertainty. Is that fair to say?
Yeah, exactly. So no experiment has ever recorded irreducible error in the electron mass or the proton mass. So as far as we know, these particles are absolutely stable. Of course, experiments always have some limits, right? So we don't know for sure. But as far as we are concerned, we have never reached that resolution limit.
Gotcha. That makes sense. So okay, so now coming to this, where do virtual particles enter in? It seems kind of like these two concepts that might seem unrelated at first, but how do we relate them together? Like mass not being necessarily there being irreducible under error around measuring mass, and then like this concept of virtual particles. I guess maybe we can start by describing like where do virtual particles come in, and then kind of relate the two together.
I think we can tackle that through quantum physics. So first, you can try to understand why the mass varies. The best way to understand it, I think, is through the uncertainty principle. You realize that the equation of subatomic physics actually doesn't require the particle to have that mass, unless you kind of let it live for a long time, of course. But in a lot of times in quantum mechanical processes, interactions happen very quickly, right? Like imagine a particle comes in, I don't know, hit my hand and comes out. That interaction generally lasts, I don't know, a fraction of a second. I don't know, depending on type of interaction it is. And people notice that, hey, when that happens, the requirement for a particle to have a particular mass kind of doesn't need to be there. And it turns out that so interactions could happen when particles don't have a particular properties, even though that's what defines particles. But because of quantum physics, you can loosely think of it this way. Quantum physics kind of allows anything that could happen to happen, and as a result, when interactions happens, there's a little more wiggle room in terms of the properties of a particle in the intermediary stage. So when that happens, I think we call those intermediary particles virtual particles.
So when an interaction happens between two particles, then what you call the exchange, the particle that's exchanged, or like how the interaction happens is mediated through this thing called virtual particles. Am I understanding that correctly?
Yeah, I would say so. I don't know. I think is that fair to say, Mikey? And the intermediary.
Yeah, I think so. Yeah, but I guess that actually brings a question up that I have. So I mean, I think what we're getting at is kind of that this kind of relates to the observability of the particle, right? Like when we measure the mass of the electron, we actually, like, for example, in a particle detector, let's say, we actually have the electron going through some detector material, and that detector material basically kind of breaks the electron apart into like a bunch of photons and other particles, and we sort of use that to measure the mass of the electron. And typically that's how detection always works, right? When we detect a particle, like especially like for the Higgs, right? The Higgs boson decays so quickly, we never actually directly observe the Higgs boson. We observe kind of the decay products, and we kind of reconstruct what the mass of that particle must have been based on what we see it decaying into. How does that play a role in the virtuality of a particle? I'm a little bit rusty on this.
Yeah, no. I think that actually brings up a good point. Like one thing about virtual particle is that they're typically almost never measured. Like you can never really measure a virtual particle, right? Because if in some sense, if you do, it will kind of have the wrong property, and that's kind of messed up in a little bit. But then you can ask, well, what about the Higgs boson, right? Like the Higgs boson has different mass. Isn't that kind of messed up? Well, the thing is, we never directly measure the Higgs boson. It's not like an electron. You could argue that you could grab an electron and just weigh it, kind of, right? But you can't grab a Higgs boson and weigh it because it's going to decay. By the time you put it on a scale, it's gone. So the way we measure it is to grab the thing that comes out and then make an inference on the intermediary. That's how we get the Higgs boson. And you can argue that because the Higgs boson, it's always kind of an intermediate state. In some way, you can almost argue that it never really existed in the first place. So it was always virtual. Again, I think this line of real and virtual particle is a little bit blurred. But a virtual particle generally doesn't get directly measured.
Wow, nothing is directly measured. So everything is kind of a virtual part. I mean, it's like it almost makes more sense to talk about the degree of virtuality of a particle rather than like think about it as like a hard distinction between real and virtual.
That is interesting because you don't actually like when Tim is talking about grabbing an electron, you can't actually grab an electron. You have to like interact with the electron. Is that correct?
Yeah. And typically these detectors, like when an electron hits a detector and we try to weigh it just sprays out. It basically emits particles of light. And you basically kind of look at that pattern and then trace back and infer the amount of energy or mass of the original object.
Yeah, and actually in calculations, we do have this concept of virtuality. I mean, it's a technical concept, but it literally is a quantity quantifying how much away from a real particle it is, right? And for an electron that existing in real life, it's zero. For a Higgs boson that you grab, it might be a small. I mean, I think that number is measured in energy square, just like the mass square that it deviates from. So for a Higgs boson, it might be like, I don't know, 10 times the mass of proton square, something like that. And depending on the situation, the virtuality can vary. So it's a continuous thing. It's not black and white.
So I guess like I want to kind of connect these two concepts together. So these virtual particles are things we can't measure directly because their properties may not be consistent. And then we have on the other side like things that don't exist for a long period of time are unstable. And so are you saying in some sense, because they're not stable, they can be akin to virtual particles where the properties aren't exactly consistent? Is that what you're going for?
Yeah, I think that's exactly correct.
Okay,
I think
okay.
that's fair.
Could could we talk about maybe even like I mean within quantum physics, but like way back in like in classical physics when I learned about electromagnetism, let's say you have a charge like staying still, it's emanating and electric fields emanating from it, and you can feel like repulsion or attraction. And then later on in electromagnetism, you learn that when you accelerate charges, then they emit light that you can actually see and observe. But electromagnetic fields themselves are made of photons. So if I have a charge that's just stationary and it's emitting an electric field, why can't I see those photons that are coming out of it? Are they even coming out of it, or like, how do I think about that?
Yeah, so this is kind of the I guess the slightly more confusing aspect of particle physics, right? Because in particle physics we always talk about particles, left
Mhm.
and particle right. But of
Mhm.
course we have phenomenon in our everyday lives that isn't exactly great to describe by particles, right? Like for example, I took a magnet and I took two magnets, they feel each other. Like I don't see particles shooting out from the magnets, right? Like what the
Mhm.
heck? Um, but keep in mind that particle is just a language. It's just like ultimately what's important is the force field themselves. Particles can be thought of as particular excitation, like wiggling, particular wigglings of the field themselves. So if the magnetic field is kind of wiggling, you can say, hey, then there's some particles coming out. But of course, if the magnetic field is not wiggling, well, you can say, well, are there no particles coming out? Well, you can still use the language of the particle, and in that language, there could be particles because the wiggle because every particle requires some kind of wiggling, right? If you
Mhm.
don't have wiggling, well, there's no particle. But maybe these aren't exactly real particles. You can think of them as kind of like virtual particles. But at the end of the day, there's really no difference, right? Really, there's some the quantum field themselves has something in it, basically, right? There's a non-zero magnetic field. So
Mhm.
that's a fact. I mean, we can interpret it as there's some there's some photons coming out with some maybe they're virtual, whatever. Or you can think of it just having magnetic fields coming out. So both are valid. So I would say like the language of particles sometimes is interpretational.
Huh. Mikey, do you have any thoughts on that? Like in terms of like using the language of particles to describe this like, like a static electric field.
Yeah, I mean, what I want to say, I'm a little bit hesitant to say, is that kind of like the common thread here is the fact that like when we call a particle virtual, what we really mean is that we're observing kind of we're indirectly observing its effects as opposed to like distinctly observing the particle itself. Um,
Mhm.
and so, like, yeah, even though we can't actually see, even though we don't actually, like, when we measure some kind of electric force, um, according to the laws of physics, that electric force is created by literally an exchange of photons, an exchange of particles of light. We don't directly observe those particles of light, but we indirectly observe them through their effect, which is the force. And so those particles would be called virtual, I guess. Whereas if somehow, yeah, if you actually accelerate the charge and actually emits a photon, you can actually observe that in a detector, and we would call such a photon a real photon as opposed to
Mhm.
virtual.
I see. So actually, coming back to what you were saying, Mikey, about like, isn't like an electron like, virtual in some sense because you don't like actually touch it, like you have to interact with it via some other intermediary, but the properties are consistent. Could you say like properties themselves are virtual, like charge, for instance? In order for me to figure out what charge is, I need to like, figure out what electrostatic forces are, other means of measuring charge, but I can't like actually like, see what the thing is directly. Like all these properties I need to infer by like interacting. So I'm wondering, like, are they virtual in some sense? Like, do they actually like
Um,
exist or?
oh, I'm tempted to say that charge is like a real property, and that energy is kind of like the property that defines the virtuality of a particle. Tim, is that too strong?
I guess Tim, what are your thoughts on that?
Yeah, I mean, we have an episode before talking about how particles are doomed. Like I know to viewers who are not familiar with quantum physics, it almost feels like we're going in circles here. But keep in mind these particle physics theories, they are very hard. We actually don't have a mathematically consistent framework to even talk about these. So a lot of these things, like whether a property exists without errors or not, these are actually very blurry concepts. I would say, yeah, even if you really dig deep into it, does the charge of a particle really exist? You can argue that, yeah, it's the way we measure things. It's only an approximation always, because in quantum physics, everything affects everything else. So like mass, charge, and everything. There's always some irreducible error. So from that lens, if you go to that direction, yeah, there's always, like the virtuality of a particle, like real particle doesn't really exist in that way. But for all practical purposes, I think they do.
But charge is more of a quote unquote real property than mass or energy. Like it's like I'm having trouble making this precise, but
Yeah, I would say
my
mathematically they
feeling is that this
are.
is true.
Yeah, because mathematically it's defined to they only have +1, -1, right, or +2, some multiples of
Yeah.
some numbers.
There's no
But
uncertainty principle for charge.
yeah, but experimentally you can argue that, well, the way you measure charge, you have to pass an electron through something. And there's always some error there, right? Like,
Yeah. But that can always be attributed to experimental error, right? There's no theoretical error. The theoretical error on the value of the charge is
Well,
zero,
if you
right?
add gravity in, I think there's always some irreducible error.
Okay. Well, when you add
But
gravity in, who knows what happens?
yeah. Well, anyway, that is the difficulty with gravity in quantum physics. When you add gravity in, everything becomes approximate. But let's
Yeah,
not dig into that.
let's ignore gravity.
Yeah.
Okay.
I would say for practical purposes, for everyday practical purposes, yeah, charge is a much better quantity, I think.
hmm Gotcha. So I guess okay. So now kind of like taking a step back and looking at kind of how we arrived at here. We started discussing that particles are these distinct entities with consistent properties, or rather, real particles are distinct entities with consistent properties. Virtual particles you can't measure, but they are these like entities. I don't know if you want to say distinct entities. It's difficult to know because you can't actually measure them directly, but they have inconsistent properties in a few other places. So I guess like what brought about the motivation to even like suggest that virtual particles even exist in a certain sense? Like what do any of you know the history of like the mechanism of how they came about?
I think part of it is comes from Richard Feynman, right, and the Feynman
I,
diagrams,
I would say, I would
perhaps.
say, I would say, yeah, I would say it all comes from Richard Feynman. I
Yeah,
mean, the idea that you can kind of like calculate the probability of something happening as the sum of all possibilities, um, which I guess is kind of a whole episode in and of itself should be. But um, yeah, it just happened. Well, okay. Sorry, Tim. Do you have any? I'm about to go off on a tangent if I don't
yeah.
control myself.
I mean, I think this language of virtual particle is a way to aid our understanding, although it does create confusion. Like when I first learned particle physics, for example, in the language of Richard Feynman, like why do an electron and a proton attract each other? Well, it's because photons get emitted by the proton and then get absorbed by the electron. But these are virtual particles. You can't really see it happening. I mean, of course, if you're a new student, you'll be like, where the hell are these photons? I don't see them. You get very confused. But if you're a practitioner about, in particle physics, you'll be like, when you mention that, I know exactly how to calculate this effect. Because if I draw the Feynman diagram that says, hey, there's a virtual particle emitted by the proton getting absorbed by the electron, that literally leads to the exact calculation I need to do to plug into the computer and get the answer that I'm looking for. It'll give you the effect of electrons orbiting a proton. So I would say its utility is mainly from the mathematical side and from this language of Feynman diagrams that has become so ubiquitous in particle physics.
Mhm. I see.
Yeah, I would venture to say that like the great insight and great genius of Richard Feynman is the fact that he kind of discovered that if you assume that virtual particles can exist, and if you do calculations, mathematical calculations using these virtual particles, you get exactly the right answer. And it's totally shocking that this should be true, but because it works so well, we just assume that it's true.
Is that the case? I mean, I know we mentioned to ignore this, but is that the case with gravity? Like just a one line answer, like, or does it break down?
No, it works. It works.
No,
And
yeah, Feynman's rules definitely extend to gravity.
yeah, and the way, I mean, this is a way of interpretation, right? You can say, well, how come I'm stuck on Earth, right? It's because the Earth is constantly emitting these virtual gravitons, and I'm keeping absorbing them. That's why I'm stuck on this Earth. But I want to emphasize one thing, that it is interpretational. It is technically plausible to get the answer without mentioning any of this. In some cases. So it's not required.
Yeah, in fact, people might know that. Yeah, people might know that Richard Feynman didn't win the Nobel Prize by himself. He actually shared the Nobel Prize with a dude named Tomonaga, and Tomonaga got the exact same results, just mathematically, without any kind of reference to these kinds of virtual particles. It was just pure equations. There was no pictorial interpretation of it, and yeah, totally up to
Oh,
interpretation.
oh, very, very interesting. So I guess then is it safe to say that these virtual particles just don't exist? Or like what would be your take on that? Like, do virtual particles exist?
Ooh, that's a tough one. Um,
I would say they do. I mean, to me, the language that Richard Feynman came up with to describe these processes, and the fact that they have this very clear pictorial um, interpretation is can't be an accident, right? There's something deep there, I think, that makes it physical.
I guess Tim, before you say your answer, Mikey, I remember a few episodes back, or maybe several episodes back, you had said like if you can't measure it, does it exist? And so if you can't measure it, like I pose the
Yeah,
question to
the
you,
tree
does it
falls.
actually exist? Yeah.
Well, well. I think we go back to like the example with like with the electron. Like there's degrees to which, yeah. So it's not like nothing is ever measured directly, as we've been saying, right? But some things are
Mm,
measured more directly than others, and things that are measured more directly than others are, in a sense, more real than things that are measured more indirectly. So, in that
mm,
sense, I wouldn't say that virtual particles. I would definitely say they have some physical existence, just not to the degree that quote unquote real particles have a physical existence.
mm.
So
All right,
basically take
Tim.
my old answer and just make a continuum from one answer to the other. And that's where virtual particles sit.
All right, Tim, you go ahead.
yeah, I think I'm inclined to disagree. Personally, I would hope to say that virtual particles don't exist, or
You
particles
just
for that
declare
matter.
calculational crutch.
Yeah, I do uphold this principle that if you can't really measure something, it doesn't really have a physical significance. I mean, does it mean that it's useless? No, I mean, it has huge, it builds intuitions, right? But I think that because, I mean, in the particle physics research field, there is a push to try to move beyond thinking of particle physics as just particles interacting and organizing your calculation this way. There has been heroic calculations where, if you think of the calculation in terms of particles, you get like 5 page and like a 200 line results. But if you use other techniques, you get a 1 line answer. And some of that gives you a hint that, hey, maybe this paradigm of Richard Feynman's paradigm of using particles, virtual particles, and whatnot, might not always be valid and might not be the best description of nature. So personally,
For sure, yeah. I mean, Tim's view is very postmodernist, I would say. But okay, no, but then I would push back by saying, okay, if virtual particles aren't real, then in the frameworks, so yeah, as Tim mentioned, there's been a big push to try to like reformulate physics without even talking about particles at all. But in that sense, it's not like real particles don't have an existence in those theories either. So I would say virtual particles are at least have as much physical significance as real particles. What you're saying is that particles might not even have any significance at all. Like that whole language might be just, approximation.
well, I think we need to wait. I think we don't have a good replacement yet. So we'll wait and see.
I'm willing to stand on the conservative side here until further notice.
Yeah, that sounds good to me. So we're almost at time, so I want to give you guys a chance to leave the audience with any few parting words, life lessons that you've gotten from virtual particles. I guess Mikey, you go first.
I feel like that was kind of like the closing statement, right? Like, so there is kind of these two viewpoints, I would say. And if you talk to particle physicists, there's generally like two camps, which I guess me and Tim sit on kind of like opposite sides of, but probably close to the middle in terms of whether or not virtual particles have physical significance, or whether or not we even need the language of particles to talk about physics. But as I said, yeah, I guess in this topic, I'll tend to err on the conservative side. And just stick with good old Feynman and say that, yeah, virtual particles are physically real.
Yeah, I would say this question kind of pushes to the boundary of what particle physics can do. And unfortunately, it is a murky science. Like we don't really have a totally concrete and solid foundation. But that also means
it's the least murkiest.
It's sure, it's true. That's fair. That's fair. But that all also means, on the positive note, it also means that there's so much remain to be discovered, right? So, and at the end of the day, virtual particles, not virtual particles, it's just a name, right? If it helps us understand physics, I think it's helpful. I think we shouldn't be too pedantic about whether something's real or not. And I don't think particle physicists are. We just use whatever's available for us to help us understand physics. And if virtual particle is helpful, yeah, it's great. I mean, we do use it all the time. So
yeah, that makes sense. I mean, it seems even though you both are on like different sides, I think both of you would agree like they are useful for what they're needed for, even as a calculation tool, or even if they exist. All right, then.
yeah.
Well, yeah, on that note, I want to thank everybody for joining us, and we'll see you all next week.